And the idea of cooling atoms depends on what we say, the mechanical force of light. So light can be particle, can be a wave. The duality here plays an important role. And let's take a simple example of fluorescence spectroscopy problem that we can cover here. Recall that if I have absorption in electronic state and also stimulated or spontaneous emission first, we can calculate in the mean number of fluorescence cycles. You can look at it, for example, at the Jablonski diagram. You can find that you can have 10 raised to or power 8 cycle per second. Okay, the number of the mean number of fluorescence cycles here is actually 1 over t. So the time or the mean time is 10 raised to minus 8. Okay, so the mean velocity of atoms and the delta v, the difference in velocity, is also can be seen like this, which is 1 over or 100th meter per second. It means that if I would like to calculate the mean acceleration, it means that I just divide the velocity per time. So the time is 10 raised to minus 8, so it covers this quantity, which is about 10 to or power 6 meter per second square, which is a quantity compared to the gravitational acceleration is about 10 raised to 5 g. This is huge pressure, as we say, on the atoms. So you can exert so much pressure to stop the atoms or to press on the atoms by these forces of light. So the main scheme of, I won't recover the laser cooling techniques or the light cooling techniques here. You can counter propagate lasers from two sides of atoms that are moving, and you can slow them down, and there are many things that we can say about this, but the cooling techniques here, I just present them quickly. If you'd like to know more information, you can go to this book, Advances in Atomic Physics by Claude Cohen-Tanuji in 2011. You go to chapters, I mentioned the chapters 13, 14 and also 12. So going back to this nice illustration here, I stole it from Claude Cohen-Tanuji, that looking at the temperature scale, you can see the sun in a Kelvin temperature is 5,000, about 5,000, close to 6,000 Kelvin. Water can boil in 373, and you see liquid nitrogen, liquid helium even, and the coldest background of the universe, about 2 Kelvin of the cosmic microwave background radiation. For Doppler cooling enhances the idea of Doppler limits of the, or Doppler shift of the atoms by laser. So you just, the scheme is like this. And then Sisyphus cooling was discovered by Claude Cohen-Tanuji in 1986, and they reach a temperature of 0.001. This is 10 raised to minus 4 Kelvin. And then evaporative cooling, which was the step to begin to realize such quantum gases. So we still cool down and down until we reach a limit when even quantum gases started to appear, and this was awarded the Nobel Prize in Physics in 1997 to guys of Stephen Chow, Claude Cohen-Tanuji and William D. Phillips, and they were awarded for the enhancement of mechanical forces of light to laser cool the atoms down to micro and nano Kelvin temperature. Nano Kelvin temperature started to appear when evaporative cooling was merged with the laser cooling, and the Nobel Prize in Physics to Wolfgang Ketteler, Eric Cornell, and Carl Wyman for their development of the cooling techniques that enabled them to see what we call a phase, a coherent phase of matter. It's called the Bose-Einstein condensation. So you hear it a lot, and this is the base that we will be beginning our quantum simulation journey on. I won't explain so much of these cooling techniques, but I encourage you to go to check the physics, complete physics on them on this book I mentioned. Actually, the colder you move, or they moved in the history, that they began by the Doppler limit. Recall the Doppler limit for cooling is that you have the KT, thermal Boltzmann equation, is actually equivalent to h bar, just this factor over 2. This factor is actually gamma here is the delta energy, which is about h bar over 2 lifetime of the molecules, or the atoms, or lifetime of the particle. So just this difference in energy that you can have for full width to have maximum in the uncertainty relation to a Gaussian, for example, of energy here. And then they moved colder and colder. Doppler limit cooling started by Stephen Shu, and then moved to William D. Phillips to realize, or Bill Phillips to realize the sub-Doppler cooling. They moved colder and colder and colder until Kulut-Kuhintanuji for sub-recoil cooling here. And then by evaporative cooling to laser cooling, they started to realize what we call the coherent phase of matter, or the coherent matter wave, which is about close to 0 Kelvin temperature. This is truly amazing that they realized such important phase of matter, which is called the Bose-Einstein condensation. So this was just a flavor for what should happen for this nice field and what happened actually. So by this way of merging the cooling techniques of laser cooling and evaporative cooling to realize the Bose-Einstein condensation, you can do really interesting quantum physics. And this quantum physics is interesting when the relation of the de Broglie wavelength of a quantum particle relative to the interparticle distance is larger than or equal to 1. And therefore you can realize the quantum effects much noticeably. For here, they moved from the laser cooling to the evaporative cooling, and then to realize the BEC. It just had some problems at the beginning, that they need more phase space density, which is actually smaller density than real matter eventually. But the combination of both allowed us to move from Kelvin, from micro Kelvin even, to nano Kelvin, or from 300 Kelvin from the beginning to the nano Kelvin temperature. The Bose-Einstein condensation and the coherence together form interesting physics at the ultra-cold limit of temperature. You can also do some cooling, some cool stuff, some fancy stuff. If you rotate a quantum liquid in a harmonic trap, for example, you do not see the classical velocity distribution. You just see some quantized effect because of the matter wave. If you say that this is the matter wave that you have, so if you take the contour or integral of the velocity here, you can recover, this is the velocity times the 2 pi r, let's say, fitted with a circle, and you have to know that this is the r, so okay, this guy here, 2 pi r is equivalent to 2n lambda. So you quantize the wavelength, or the Broglie wavelength, which is the de Broglie wavelength is the h over mv. Okay, so eventually you'll find that v times 2 pi r is nothing else than h over m, and this is quantized also. So you can really see, if you rotate a quantum liquid, you see quantization of the this nice quantum harmonic trap here. So let me tell you eventually something about the bosons and the fermions when you cool them down. The cooling down of bosons realized by, for example, bosons like sodium and rubidium, you cool them to the ground state, and the ground state looks like this in the Bose-Einstein condensation. So this is the Bose-Einstein condensation. Here, if you get a fermion and you cool, so you make some homogeneous distribution here, and this is a Fermi gas in the system. This is a Fermi gas for fermions, and you can play with this nice Fermi gas also. But let me tell you that BEC at the ultra-cool limit of quantum gas can realize many or can feature many characteristics in the physics world. You can study quantum optics at the ultra-cool limit, some also cold chemistry, quantum metrology. You can isolate the effect of the temperature, you can isolate the effect even from the environment, and you can realize some precession measurements, some collisional physics. Okay, let's begin that from the ground state, and you start to raise it one by one. And eventually the topic of our interest is strong correlated physics for realize even this is strong correlation physics you can do by quantum simulation of many body physics here by Bose-Einstein Condensation, nice phase of matter. Thanks for watching, and see you in the next videos.